class name. So it's my great pleasure to be here in Harishchandra's Research Institute because Harishchandra was and he still is my mathematical hero. And my work was inspired by the ideas I learned trying to understand his work. So let me make a personal note that I was studying in Croatia and theoretical physics, and at that time it was fashionable to study representation theory of some small dimensional semi-simple Lie groups in physics. And I got fascinated by this subject. And my advisor was, of course, also a physicist, but he was a student of Julio Reger, who was at the time at the Institute for Advanced Study in Bristol. And my advisor spent there 2 years, and he said, if you want to learn this subject, you should start reading works of Harishchandra. So I started reading Harishchandra's papers. Nobody at the department could help me at all, but I think I managed to learn something about this, and I will try to prove it. So, okay, so this is, I should actually start talking about math. And so what I plan to do today to discuss some part of history. So basically how Harishchandra got from, say, unitary representation to Harishchandra modules and why he did that. And then we are going to study in next lectures category of Harishchandra modules. So there are matrix coefficients, there are asymptotics, and related things Dipendra Prasad was discussing in his introductory talk. So let me try with prehistory. So let's denote by G naught a connected semi-simple Lie group with finite center. I mean, everything I will be discussing can be done for Harishchandra class of groups, which we have discussed in Dipendra's lecture, but just to simplify notation and all kinds of technical tricks, I will stick to this. And from Raghunathan's lecture, I mean, I am trying to use the material discussed already as much as possible. He said that if you want to study, say, unitary representations of this group, we have the action of the group on a vector space, and we consider this map. And if representations are finite dimensional, then there is no problem because finite dimensional vector spaces have essentially unique topology, Hausdorff topology, just a natural one. But if, say, V is a Hilbert space, or say, if you want locally convex space, then you have a topology on V, and then the definition of representation involves the continuity assumption of this map, and then under certain conditions, this can be replaced by strong continuity of the action on vectors. So, if V is finite dimensional, then if I consider this representation, so let me call this action pi. This is actually the action of representation. Pi of G, pi is a continuous homomorphism into general linear group of the vector space V. This is a Lie group, and as we said, this this thing is continuous by theorem of Cartan. It's automatically differentiable and actually real analytic. So you can differentiate this action, and again, I will denote by G naught the Lie algebra of G naught, and by G the complexification of the Lie algebra, and we get the Lie algebra of GLMV is the Lie algebra of all linear maps on V. So basically, by differentiating this pi, we get a finite dimensional representation of this complex sensible Lie algebra into matrices on V, and say if G naught is simply corrected of pures, we can go back. And then actually the analysis of these representations becomes an algebraic problem. And also say if G naught is compact, then as we have heard in Raghunathan's lecture, first of all, any irreducible unitary representation is a Hilbert space sum of any unitary representation is Hilbert space sum of finite dimensional of irreducible unitary representations. They are finite dimensional, so they have this algebraic nature, and we completely understand the situation. We understand unitary representations of the diagrams. Harishchandra was, of course, interested. This, as far as I remember, was a problem assigned to him by his teacher in Iraq to apply this to the Lorentz group. So say SL2Z if you want, and this is a non-compact group. So there are technical issues in this sense, and he embarked on this project to understand the representation theory of these groups. At that time, it was known, and I don't know exactly the reference. I think Bartasarati mentioned friends yesterday, but there was definitely the abstract decomposition of unitary representations into a direct integral of irreducible was understood on functional analytic level, and it gave a unique decomposition of a representation in case the group is type 1. And one of the results, Harishchandra proved that this type 1 holds in our situation for semi-simple groups. But again, so Harishchandra was aware more or less that the goal is to understand irreducible unitary representations, because all unitary representations are built outwards. But this problem is kind of difficult, and let me try to explain why. First of all, our space where representation acts, so there was another theorem which was proved in more or less the same time. It's, say, an interesting exercise in structure theory. If you take a simple Lie group, which is non-compact, and look at its finite dimensional representations, then those finite dimensional representations are just multiples of trivial representation. This is the theorem of Siegel and von Neumann. And if you think, say, well, SL2R, and look at a subgroup A0, 0, A inverse, you can describe finite dimensional representations of this by discussion I was mentioning before. Go to Lie algebra, complexify, and then use standard tricks to find representations of SO2R. And then you see that those matrices act in other representations as diagonal matrices with powers of A on the diagonal. Now, if you have A is here, I should say that A is strictly positive. If the powers are non-trivial, so start from n to some minus n, and then those functions blow up at infinity when A goes to infinity in the group, and therefore matrix coefficients are blowing up. And matrix coefficients of unitary representations have to be bounded, please. So, n greater than 1 cannot appear, so basically you get just identities, and this has to be trivial representation. So this is a sketch of the proof of this thing. Special case, general case, essentially can be proved using the same idea. Any questions? So this example shows that if you want to understand representation theory of a non-compact semi-simple Lie groups, you have to study unitary representation, infinite dimensional representation. Okay, if you have an infinite dimensional representation, a unitary representation of G naught on a Hilbert space, then you cannot differentiate the representation. The action G and G on pi G V is a continuous function, but it's not differentiable. And therefore, in general, you cannot differentiate this map in this case and get the representation of Lie algebra. There was a known statement in that time that differentiable vectors are dense, and this used the idea the Pendra was mentioning. If you take this function and integrate it over the group with respect to R measure, where this is C infinity with compact support function, then you get a vector which is differentiable, infinitely differentiable. The function becomes infinitely differentiable, and basically, if I take this Dirac sequence of functions around identity, where the integral of this is 1, I mean those, when you're shrinking this support, these vectors are converging to V, and you can show the differentiable vectors are dense. So this was a I think, known observation. But this was not good enough, because if you have a differentiable representation, then you differentiate the action, you get the action of Lie algebra, but you cannot go back. You can write down Taylor series of a matrix coefficient using Lie algebra, but the Taylor series do not have to converge. So Harishchandra had an ingenious trick how to do this. He said, okay, the problem is that this delta sequence, you can say, it converges in distribution toward the Dirac delta distribution, can be built out of real analytic functions. So on Rn, you take these Gauss packets in the analytic, and if you squeeze them, they give you a delta sequence. And he used the Iwasawa decomposition and this trick on An, and then twisted with K, and he proved that analytic vectors for this, which this function is real analytic but dense in the unitary representation, actually in Banach space representation, but I don't think this is relevant too much for the purpose of this discussion. So, but the question, and this also proved that analytic vectors are dense. But analytic vectors are invariant at the group action, but there are some objects we don't understand at all. And this is where Harishchandra did another important step, which was critical for development of the theory. So, if you denote under these conditions, so the center is finite, so there exists a maximal compact subgroup of G naught, and all maximal compact subgroups that are conjugate. So Harishchandra's remark was, let's take our representation IV on a Hilbert space and let's restrict it to maximal compact. One maximal compact. Doesn't matter which one you pick. Then, by Raghunathan's talk, you know that what you get is that our representation restricted to naught is a Hilbert space sum where this delta is in K0 head. This is a set of equivalence classes of irreducible finite dimensional representations of K0, and you know that they are all unitarizable. There is, as Dragan explained, there is a natural inner product which gives unitary structure to these representations. And then I will have the space of representation delta times some multiplicity, which can be finite or infinite. And now, the second observation was, if you take an analytic vector in V and project it by the projections Dragan was describing to one of these isotypic subspaces, then this vector stays analytic because you take the vector, you multiply it by a character of irreducible representation to integrate this state to an analytic function, and therefore from denseness in a space V, it follows that analytic vectors are dense in this space. And then the first important, deep, there are a lot of important steps, but the first deep result of Harishchandra was that if V is irreducible, then all of this M deltas are finite. So, if high V is irreducible unitary representation, then M delta finite for all deltas in this unitary group of maximum itself. Harishchandra called such representations this property that multiplicity is a finite admissible. IV is admissible. And this means if you.
Can you explain why this is
Excuse me?
Why am
Why is it finite? This is a deep theorem. This was just for his first Harishchandra big result. I will get to this in a different way than Harishchandra in maybe second or third lecture. But at the moment, I am just quoting this so that you see why the notion of GK module or Harishchandra module is the right one for our theory.
So if you go back to the right direction, it's a UG module.
Oh, I will get to this. You're going ahead of me. Because, Dragan is 100% right. I just wanted to write this means that Om from K of U, if U is some finite dimensional representation of K into V restricted to K is a finite dimensional vector space. So now the first observations before Dragan's claim is that once we know that representation is admissible, then we know that all of these vectors are analytic because of denseness state. So it is a big leap forward because we know the algebraic sum of all of these guys is definitely dense in the Hilbert space V, and these are analytic vectors, and they are well understood as the K naught margin. And then the following thing makes sense. We say that a vector,
What is U over O?
excuse me,
Homomorphism of U. What is a U?
U is any finite dimensional representation of K. It's enough to check, of course, that they are usable because of semi-simplicity. But I mean, this is just, you will see at some point this will appear in higher, in different disguise. So the vector B in B is a K naught finite if the orbit spans a finite dimensional vector space. So, if our representation is admissible, then the algebraic sum, so here let me denote Hilbert space sum here with a hat, and this will be just the algebraic sum of n delta v delta. These are all K naught finite vectors. In now, we can do the following. So let's let me call this the K naught finite. So this is the space of all K finite vectors in B. We already remarked that it's dense. And now we get to this situation that the action of the Lie algebra on here I take adjoint action, here I take the natural K of K naught action, and then the action map into B becomes K naught equivariant, and all the vectors here are K finite, so here we land in K naught finite vectors. And this is Dragan's remark. So this tells us that the space of K finite vectors is a module for the Lie algebra and for compatible with K naught. And then if it's a module for the Lie algebra, we can extend this action to the envelope in the algebra G. So we have U of G module, V K naught finite, which is also a K naught module. So it has two actions, and there is a compatibility condition. Then, with our assumption of the group, action of K naught, of course, as a maximal compact. And since the space of K naught finite vectors is a sum, algebraic sum of these representations, so we can clearly differentiate this and get the representation of Lie algebra of K naught. And the Lie algebra of K naught sits in G naught, so it sits in G, so it sits in analog Lie algebra. So we want that these two actions of the Lie algebra of K naught are the same. So this is the compatibility condition. If we are dealing, say, with Harish-Chandra class, we have to be a little bit more careful, but this is a minor technical issue. Any questions? So now we are at the central point of our discussion. Now we can define GK modules, and I want to discuss this briefly because, okay, before I make a formal definition, let me point out that if you think about this for a moment, I constructed a functor from unitary representations, under certain conditions, to this UOGK modules. So, but let me make the more specific the definition of the category. So I will call GK module the module, so say pi V. So V is, there is no topology. This is completely algebraic object. Is a vector space or C. It is a U of G module. Secondly, it is an algebraic A naught module. What does this mean? That V is a union of some family U where these are finite dimensional K naught invariant subspaces. So this is, in a case of K naught, because of semi-simplicity result, Dragan mentioned this is equivalent to this condition. I am just formulating this in this way since GK modules, I have to explain why I should put 0 here, but I didn't do it, and I'll explain in a moment why. So this can be generalized to not necessarily compact groups. And such category of modules are important in representation theory. For example, a similar category, if you replace K naught with a Lie algebra of N, say upper triangular matrices in SLN C, is essentially highest weight category with some assumptions. So the theory we are going to discuss apply in all of these situations. And then the third condition is compatibility. So, okay, let me address this question of norm. Since in the second lecture, I will be explaining the proofs of these results using some using D-module technique, and D-modules objects in complex algebraic geometry. To be in the right category, we should replace K naught with its complexification K, complex algebraic group, which has its Lie algebra is complexification of Lie algebra K naught. And but again, because of the result Dragan was discussing, this is just a formal modification. So I want to be able to talk about the GK modules without norm. I won't be doing this today. This is one remark. The second remark is you will find these definitions with various additional finiteness assumptions. And I don't want to do this now, I will do this later, but this super general situation is useful if you want to develop homological algebra machinery, because then you have freedom, you don't have to worry about various finiteness statements. So you basically, as you will see, you develop machinery for GK modules, and then you impose additional conditions on finiteness and various other and admissibility, and you get theorems we are actually interested in and we are applying in proving real theorems. Okay, so linear map between two GK modules and two GK non-modules which intertwine both actions are morphism in this category, and we have this category M G K naught. So this is more or less what Harishchandra reduction, which is in Harishchandra. So there were some technical conditions I will mention today or tomorrow, which appear there, but maybe I won't do it right in chronological order, but I think this will make sense with respect to the proofs I'm going to sketch. So this is clearly an abelian category, and as I said, we can do various cohomological construction, like cohomological induction Arvin will be talking about, using this category and its properties. So, what was Harishchandra's plan? Harishchandra realized how from unitary representations, say reducible unitary representations, you can get to GK modules. Now, he also figured out that this is, of course, he liked this fact because this is a category of algebraic objects. You don't have to worry about analysis in this category. But then he observed that if I take say a GK module, a GK naught module, which is infinitesimally unitary, so this means that there is an inner product on this space with respect to which the action of K0 is unitary, and the action of the real Lie algebra G0 is given by skew-adjoint linear maps. So this means infinitesimal unitary. Then, if I take such a module, and if it's irreducible, then the completion of GK module with respect to this inner product is a Hilbert space, and one can extend the action using Taylor series of G, because the vectors are analytic, to, I mean, if it came from unitary representation, and when we extend this action, we recover the original representation. And now if you are, I mean, I will discuss this later, even if we have GK module under certain conditions I will discuss, you can construct its matrix coefficients, and then you can construct your representation, and if original representation is infinitesimally unitary, then the final product is unitary representation. So Chandler's idea was, let's understand these representations, and then we can try to understand this, and then we will understand all unitary representation. So what was accomplished using, say, Langlands' work of, Chandler, of course, for discrete series, for temporal representation, and then Langlands for non-temporal representation was to classify irreducible GK0 modules, and this classification of unitaries is work in progress. As you know, Dragan and his collaborators have a program which can calculate those. The problem is that we cannot build computers which can actually run this program for arbitrary GKs. So we can solve some examples, but we are stuck with others. For example, I think probably one can solve maybe even this E8 example, which was very popular in media a couple of years ago, but definitely there is no chance we can do complex E8 because we cannot build computers which can handle so much stuff. Because basically, to do the calculation with this algorithm in a finite amount of time, everything you calculate has to be in the computer memory. And this is an enormous amount of information, and far beyond our machines we can build now and probably in the distant future. Okay, so this was kind of introduction in what I want to discuss. I want to discuss Harshchandra, GK modules, and a smaller category I will call Harshchandra modules a bit later. And so in the second lecture, I will, I think, convert this problem into a problem with all the D modules. So I will give a crash course with a lot of cheating about D modules and how they allow us to classify irreducible objects in this category. And then we are going to discuss matrix coefficients and asymptotics. Any questions?
Are you assuming that the models in the type are finitely generated as EG models?
Not yet, because at this point, I don't want to worry about this. See, I should ask Armin how he is trying to build cohomological induction. It's not that, I mean, the really this condition of finite generation becomes important when we make the assumption that representation has infinitesimal character. And this is just the next topic I wanted to discuss. Then this will lead to coherence of D modules and holonomicity. But at that point, we don't have any particular positive result if we assume this.
Condition 2, you are saying that V is a unit of these UIs.
Excuse me,
So in condition 2,
Yeah.
you are saying that V is a unit of UIs. Like the UIs are finitely k-unit subspaces.
yeah.
So can we say that these, are nothing but just the k-finite vectors and the spans of those?
Yeah, in this case, but you see, this is because here I'm dealing with compact groups, so the action on all those UIs is semi-simple. If we take a different group, different, say, algebraic group, which is done in examples which are formally the same, and the same theory applies, then you can have a group and K is not reductive, and then you really you don't want to involve direct subs. Yes, but it's yeah, it's so consider.
So complexifying A0. Say about complexity
Yeah.
of A0. So is it like the maximum compact for complexify G or
No.
so you are
No, I mean, it's just, you can, if you take a compact group and look at all finite dimensional representations on complex vector spaces, it factors through complex group. This is, say, how Bourbaki defines it, or you can just look at the theory and see that any representation of K naught comes from some representation of algebraic group corresponding to the complexified Lie algebra just by restriction. This was, I think, you maybe even made this explicit in your talk. Yeah.
It will be made explicit later next.
Yeah.
See, for instance, the complex real unitary group, the entire GLMC. U1 is a real big group. Complexified, you get it in real algebra GLMC, and GLMC is not compact. So complexification, no complex group can be compact. I mean, it is not a big.
Okay.
Any further questions? If not, let's thank Dragan.
No, we are not finished.
It's not finished yet.
Oh, you told me that I have still 10 minutes.
You can have the C mode.
Okay, I mean,
I'm sorry.
I
It's
just,
my mistake.
you see, in a way, I wouldn't mind to stop here, but
No, please
I
go.
will make the Depender unhappy because I wouldn't fill out his program from the introduction. So I want to say a few more words. Actually, it's related to Barta's question. Okay, so let me discuss this issue. Oh, so you told me not to use this, but right? So now I have to talk about another big result of Harishchandra, and this is something extremely useful. Harishchandra was the first one who understood very well the center. So this is an enveloping algebra, and C of G is center. Harishchandra studied this. He defined so-called Harishchandra homomorphism, which I will discuss tomorrow. But so this is something he was very familiar with. And in the case of unitary representations, using some results about unbounded operators, he proved that, the Lie algebra and enveloping algebra of U of G acts on the vector space by unbounded operators. I just do not like this notion, but anyway, and there was, using spectral theory of unbounded operators, you can show that C of G acts by multiples of scalars in an irreducible unitary representation. So, and this action, which is just a homomorphism of the center in the complex numbers, is called infinitesimal. And Harishchandra assumed when he was studying representations on Banach space that this thing exists. But we are going to twist this a little bit. If I take an irreducible GK module, GK not module, and it will be this G module. Since it's irreducible, it is generated by any non-zero vector as a module over enveloping algebra, because we assume that Ka naught is connected. If we have Harishchandra class, we will have to fiddle a little bit, but this is easy to take care of because K naught has only finitely many components. So, irreducible GK module is irreducible as U of G module. Then this means that if I take B different than 0, that U of G is equal to V. So V, the GK module, V is countably dimensional as a vector space. And under these conditions, you can show that irreducibility implies that anything which commutes with the action of U of G is multiple of scalar. This is Dixmier's version of Schur's lemma, I should say, in Dixmier's book on enveloping algebra. So the conclusion you get from this is that in this case, chi of p from Z of G to C, so there is this homomorphism such that pi of Z on V is just multiplication by this character, and this is called the infinitesimal character of this irreducible Harishchandra module. So now we want to make our category of GK module slightly smaller. First of all, if I assume that I have a GK module of finite length, so that it has a finite filtrations, that the corresponding graded object is sum of irreducibles, then each of them has infinitesimal character. This tells us that the center of G, the action of the center of the enveloping algebra, Z of G, on this module, its kernel is an ideal of finite codimension. So we define, okay, so now I will define a category where we put two additional conditions. So let A, G, K not be the subcategory of M, G, K naught, where objects are finitely generated as U of G modules so this is the first condition. And the second condition is that all vectors are CG finite. So basically, this implies that the annihilator of such module in the subcategory, the annihilator in the center is an ideal of finite codimension, and I will call elements of this category Harishchandra modules. And the theorem, we want to prove that these modules are of finite length. So this is the characterization of objects of finite length. And later we are going to show that they are actually admissible. And that this, in a way, closes the circle of these ideas from Harishchandra's original few papers about GK modules, or I mean, So I will call the objects here either admissible representations or Harish-Chandra features. Okay, now I'm all done. Okay. Any questions? Yes. No. For all these, this pi z acts by a multiple of identity operator on the space. So this is, yes, thank you. I should say for all z in D. Another thing, yeah, okay, so I won't abuse your time. I will talk about this.
Is real freedom is due to
This is Harish-Chandra, but and a lot of results of Harish-Chandra because so basically this is related to what you were saying that about characters. So that you attach to any irreducible GK module and irreducible Harish-Chandra module, you can attach a character. It's invariant eigendistribution corresponding to infinitesimal character. Harish-Chandra proves that the space of these invariant eigendistribution for this eigenvalue is finite dimensional. So since characters of different irreducibles are linearly independent, you have finitely many of them. And then if some of them will appear with higher multiplicity, this would ruin admissibility. So all of these ideas kind of intertwine and lead to this. And I will try to.
real freedom is due to you or
No, I mean, it's Harish-Chandra. I mean, I'm just playing with Harish-Chandra's result. I'm just trying to understand this. No, I don't want to take any credit. I mean,
I'm asking where is the freedom stated?
this is, you sound like you are a beginning student in the field. You know that nothing is written out for this whole thought theories. I mean, okay, I can try to answer. I think if you go carefully through Harish-Chandra, you will find all the pieces and you can put this together. But, I don't know answer to your question.
In the context of PID groups, this is usually attributed to process functionality.
Yeah, and in a way, I mean, if you know localization theory, I think this is more or less also follows from this, from the D-module theory. You see, the only thing is that using this, you show that for a given infinitesimal character, you have finitely many reducible representations. So this is easy, much easier than using characters. But then you have to prove that these modules embed into principal series to prove admissibility. Because in D modules, it's harder to find what are K multiplicities of the objects. So in a way, you have to do some ping pong between various theorems. But definitely, Harish-Chandra was, in his terminology, aware of all of these results, I'm sure. But he was very humble, so he was not advertising, oh, this is my theory, like some of our colleagues.
Most of these lectures are going to be made. You have a publication there.
Oh yeah, so
You
maybe
find it good.
it's a good occasion. Maybe I can